right? In this video, let's discuss something practical, how practically that happens. As of now, we are just creating such pictures, circles, and finding out where the constructive interference will happen, where the bright spots are. But in reality, this will be the picture on the screen which you will get. Right. So this is the double slit experiment result. So this is what you are looking at. So can you see there are some fringes here? So this is the bright fringe, and then you can see the gap, right? So that this gap is a dark fringe, we can call it. Then again, we are getting a bright fringe, and it alternates. So if you see the center one, this is called a special name central maxima. So this is the central maxima, means it is the brightest spot on the screen, most brightest. Okay. And as you move away, you will see it is getting faded away. The brightness is getting less and less and less. So now in this video, what we want to calculate is how much is the distance between this, the central maxima say, and the next one. Like what is this width? What is this width? So distance between two bright fringes we want to calculate. And we denote it by sine beta. So this will be called fringe, fringe width. So remember that it is just the distance between two bright fringes, right? So that is how we understand fringe width. Also, please understand that it is not only about this distance, it can be of any. So it will remain same. The distance will remain same, but because they are most brighter ones, the central maximum and the very next one, so we find the spot where we are getting maximum intensity at the center, right? Center of this brightest spot, and then we calculate the distance between them. So if I give you this screen, you should be able to calculate that, right? You can put a scale here. You can say, okay, sir, the distance is 1.5 centimeter, 1 centimeter, or 2 centimeter. So you can give me the fringe width. But guess what? We have an expression for that. We can calculate that in terms of wavelength, the distance between the slits, the distance between slits and the screen. In that terms also, we can calculate this also, and we can match whether our experiment, what we are doing, is matching with this fringe width calculation. Okay, so let's go back to the copy and let's draw some lines, but now with the practical bent of mind, like what actually happens. So being practical means let's have a real value of the slit difference. So let's say if I have a need to draw two slits here, double slits here. So I will keep the separation as 0.1 mm. So if you see your scale, that the minimum it can give is 1 mm. So I'm talking about 1/10 of that, very, very small. That much the separation will be in real around. So let's say I will draw one slit here. I can show them as dot. So you are able to see the dot. Good. Now let me draw another slit. It will be just like this. What? It looks like a single dot. They are very, very close in reality. So now let me draw screen also. So let's say this is the screen. And let me draw the pattern. So in front of slits, you get the central maxima. Let's say here you get the red color band, which we call a fringe, a bright fringe, right? After that, what will happen? We will see a black space or a black fringe. And then again, we will get the red one. And it will continue. But we can stop here. Let's focus on calculating fringe width. So the fringe width will be the separation between these and these. Let's say two bright fringes, and the distance between them is beta fringe width. So that is what our focus is. We need to calculate this. This will be formed when the slit will have waves reaching at this point. The path difference will be 0. So for this, we have path difference as 0. And in the last video we saw, you can write it like 0 lambda. And then this will be when the rays are coming through these slits meeting here constructively, and path difference between them is 1 lambda, or simply lambda. So now if I try to show you that, let me draw some rays here. So from the first slit, let's say here it reaches, and from the second slit also I'm trying to draw, and you can see they are very, very close. They are looking like they are a same line. So this will not be huge difference between them, these rays which you are constructing here. So now, but we can see here a triangle. Can you see one triangle here? Oh, this line, if I meet, let me draw this reference line. It's not light ray, I'm just doing it for my reference. So this much and this much. Okay, and this will be angle theta. This will be angle theta. And now we can see a right angle triangle, right? So the perpendicular of the right angle triangle is this beta, and the base is this line. And guess what? This is a D, capital letter D. We show it like capital letter D. The distance between the slit and the screen. So we have a triangle now, and we can assume that, let's say this angle is theta, so we can calculate some trigonometry functions. So can you tell me what will be the tangent of theta in this diagram? So tangent of theta, we know we need to know perpendicular perpendicular divided by the base. Now, this will be perpendicular is beta and base is d. So I can say tangent theta is this. So this is our first equation. We did nothing. We just saw that, these lines will meet here, and we saw a triangle here, and we calculated what will be the tangent theta. And this is giving us some information because we want to calculate this, but somehow we need to solve how to solve tangent theta. What will be value of that? Okay. So for that, what we need to know, we need to use another information which is already written here. So the path difference between these rays, these two rays, should be lambda. Now, how we can measure that? It is very small difference, right? So we are not able to see it in close up. So let us draw a big diagram like microscopic view, and let's have these slits set apart, and then we can see how much the path difference is, and that has to be equal to lambda. So that will be our approach, the next step. Let's say I draw a zoom in and I'm just seeing it closely with a magnifying glass. So I can see the slits now. 0.1 mm will look huge. So it'll be like this. And I can say this is D. And remember, when we were drawing this diagram, let me go back to that diagram. Yeah. So this diagram, if you see, these lines are parallel, right? They are coming almost parallel. So remember that. So this is the microscopic view. We don't have to draw entire diagram because we are just seeing the slits. And let's do it and draw these parallel lines. So one ray will be going here. Another ray should be parallel to this, parallel to this, parallel to this. And going forward, they will meet at the point of the fringe, bright fringe next to the central maximum. So that is the journey. So we are just interested in this path. So now, can you compare these two lines? See this line and see this line. So you can clearly see this line is covering more distance. There is some path difference. So what will be the path difference? So if we just draw one perpendicular at this point, it is 90-degree, right? So this much is the difference. This is the path difference. From here onwards, let's see this point, notice this point. After that, they are covering the same distance. But the path difference is only this. You can understand like this, if say 1 lambda is the path difference. So after that, what will happen? This will go like that. It will go. And again, this is will start like that. So what will happen there? Crest and crest will match. Trough and trough will match. Crest and crest will match. And trough will match. Like that, we can understand. Let me go back. So now after this what? So let's say it is at angle theta from the horizontal. Let's say it is angle theta. So can I understand this triangle now? So if this is angle theta, this angle has to be 90 minus theta. Because see, can you see the right angle triangle here between this and this horizontal line? Yeah, this and this. So if it is 30-degree, this has to be 60-degree, right? And this, what is this angle? 90-degree. And then what will be this angle? So this angle, let's say it's alpha. And we want to know what is this angle alpha. So in a triangle, the sum of all the angles is 180-degree. So alpha plus, what is the second angle? Second angle is this, 90 minus theta plus 90-degree will be equal to 180-degree. And then alpha will be equal to theta. So we can say simply, if this angle is theta, then this angle is also theta. So let me go back. So now this angle is theta because this angle was theta. Now, can you focus here the attention another triangle we are getting, but now when we are seeing this picture in a close up. And now, can you calculate not tangent theta this time? You can calculate the sine theta this time. Can you calculate? So sine theta is what? Let me remind you how we calculate sine theta. What we do is we take perpendicular, perpendicular divided by the hypotenuse. That is the formula. Okay, so now if you see in this triangle, this is the perpendicular. How we will be able to find it? Every time in right angle triangle, in front of angle, you will see the perpendicular. So this will be the perpendicular. Well, with the hypotenuse, very easy to get the longest length. It is here. So what this is equal to? See this. This is a separation between two slit. Put the distance between two slit, and that we denoted by d. So can we say sine theta will come up as, now what is this? This is our path difference, right? That is the path difference between these two rays, right? So this is the path difference. So let's say path difference, okay? And then we will divide it by t. Now, how much should be the path difference? Path difference should be 1 lambda. So that way we can say sine theta will be equal to lambda divided by d. So this is our second equation. We are almost done with the derivation. Now it's just a rearrangement and one assumption of small angles. Let us discuss that now. So let me revise you what we have done. First, we draw slits very closely, saw this triangle and calculated tangent theta, and we got to know tangent theta is beta by d. Then we saw the close-up of this slit and focused on this right angle triangle, and then we said this angle is theta, then this angle will be theta, and then we calculated sine theta this time. And now sine theta is coming as lambda divided by d because this path difference should be equal to lambda. Now, what we need to do is compare these two equations. So first thing, the most important note which I'm going to write here, note is for small small angles, sine theta or tan theta, they'll be all equal to theta. What do you mean by that? I mean to say, like, if I do very small angle and I'm talking about in angles in radians, so let's say I calculate 0.002, let's say theta is this, so I will get value 0.002 as answer. I will get the theta back. So this will happen in sine and also with the tan. 0.002 will should give us value 0.002. For small angles, this happens. You don't believe me? Let's see the calculator. So here is my calculator. I am going to calculate sine of 0.002, very small angle. And please keep in mind that I'm calculating, putting values in radians. That's why you can see on the left RAD, radians. Okay, so sine 0.002, what will be? Let me press the equal to button. Whoa, it is equal to 0.002. It is same as you have put the angle. What about tan theta? Let's put calculate tan 0.002. It is a very small angle for tan. So if I press equal to, again, it has become coming equal to 0.002. So we can say tan theta is coming as theta only. Welcome back. So now you believe me. So let's compare that. So tan theta is beta by d. I can say theta is equal to beta divided by d. Sine theta is equal to lambda by d. I can say theta is equal to lambda by d. Oh, we can compare. This should both be equal to lambda. So I can say beta divided by d should be equal to lambda divided by, okay, this should be small d here. It will be small d. So lambda divided by d. So now I can say beta, because we wanted the fringe width, that will be equal to lambda. What is the wavelength we are shining on, and multiplied by capital D, the distance between the slit and the screen, and divided indirectly proportional to the slit. That much is the expression. This is the expression which we were looking for. Expression for fringe width. Fringe width in which experiment? Young's double slit experiment. Thank you very much.